Yeah, thank you very much for the introduction and the opportunity for today to talk about the testing method and the quality assurance for the thermoplastics and master batches. I will tell you today some examples about pressure filter test, film inspection, and rheometer. The pressure filter test is a method which is quite often used, and we heard this test method today several times in the other lectures. And the method is in principle a melting of the polymer, and the melt is pressed through a defined melt filter, and the pressure which is built up in front of the melt filter is monitored and evaluated. Particles like contaminations, agglomerates, and pigments are stopped in the filter and increase the pressure in front of the melt filter. The main applications are the testing of the pigment or additives dispersion, but also the cleanliness from virgin material and recycled polymers. Here are some examples of standards. The ISO 23900 is a method which is used for the measuring of the dispersion, so especially for pigments and extenders. And the other two ICMBA standards, the 3218 and 6265, is used more for the test of the cleanliness of polyolefins. Here the main steps of the test procedure of the ISO 23900. First, we have to mount the screen pack, which we want to use for the test. Then we start the test line with a basic test polymer, and then we fill in the test mixture in the extruder. Then we can start the test, and after the hopper is empty, we purge the equipment with 100 grams of the basic test polymer. After the 100 grams, we stop the equipment and purge additionally with basic test polymer to prepare the next test. There are two text mixtures which are defined in the standard. This is a small text mixture with a totally 200 grams containing 5 grams of pigments. And the larger mixture has totally 1,000 grams with 80 grams pigments. The small mixture is mainly used for the test of color pigments, and the larger mixture is more used for the test of black and white pigments. This is a typical curve. At the beginning, we run with a pure basic test polymer. We have a constant pressure and measure here the so-called start pressure. Then, after fill in the material, after a short time, the test material arrives in front of the filter, and it could happen that we have first a drop of the pressure because of wax, additives, and so on in the master batch, which have a low viscosity. Then the filter pressure increases because of the agglomerates which are stopped by the filter. And then we have an empty hopper and filled in the additionally 100 grams purging material. So the pressure still increased until we get a point where we have purged out the main test sample material out of the extruder. And at last, the pressure drops, or depending on the sample, could be that the pressure has a constant level. Here, a comparison of the filter holder of the different test methods. We see here the ISO 23900 with large holes where the material can flow through behind the filter. And here is the ICM 3218, which has a quite big screen, a large area, but quite small holes. And also the number of the holes are not so large compared to the large area. The ASTM 6265 has a quite small filter and only a few holes, and only this blue circle shows the area where the material is flowing through the filter. So it's quite small cross-section where the material flows. This is an example for the test head of a ASTM3218. We see that the holder, the filter holder, the breaker plate is quite thick, and that we have to use up to 5 screen packs, and that's a quite large number in my opinion. This is the ASTM6265. We see the smaller filter holder, small filter here, and here the small cross section for the channel. This is our test head for the ISO 32900. We have integrated a valve that we can switch the melt flow in a bypass flow so that we don't have to stop the extruder when we change the filter. The filter is here integrated in the cassette system, the breaker plate here, and can be changed very quick in a few seconds. I have here a table which compared the different test methods in the main values here in this case. We see that the screw diameter is here in the limit between 19 and 30, and the ASTM standards have a larger, wider range of between 25 and up to 64. The ISO standard needs a melt pump because this melt pump generates a constant volume rate. The ASTM 3218 allows an optional melt pump, but it can be run also the system without a melt pump, and in the ASTM 6265 has no melt pump integrated. So the test amount is quite small in the case of the ISO norm standard, and we have around 14 kilograms sample material which we need for the ASTM standards. I tried to estimate the throughput of the different test methods, and you see that we have here a quite small throughput of 3.6 liters. In this case, it can be vary between 5 up to 75 liters per hour. And these are the dimensions of the filters, the diameters, the areas which we have in this case. And at last we see here the speeds of the flow speeds of the material, which is quite very different, very high at this ASTM standard norm. These are the calculations of the test method. It's quite similar what we have here from the ISO and the ASTM 3218. We have the maximum of the pressure which we measure, or at the end of the pressure, and the start pressure. The difference between these two values is divided by the amount of the pigments, in this case, or the total amount of the sample. The ASTM 6265 has not really a calculation. It's only written that you have to look at the start pressure, the end pressure, and maybe you can have a look on the pressure gradient. This are some examples for the test equipment for the pressure filter test. This is the small tabletop system with a small extruder, 20 millimeter diameter, and the test head here. And as I mentioned, we can run the system without stopping the extruder for the next test. And the melt pump generates a constant melt flow rate. Additionally, we have the possibility that the filter is preheated before it is in use. So you can really very quick change the filter in the system. Next step was to design a so-called auto sampler where we have up to 7 containers where we can put in different samples and where the system is automatically run the test loops with the materials. We also designed an automatic filter changer where the filter can be changed automatically, not manually. And this system can be mounted also to a big production extruder to check the quality of the material. And for example, especially for the area of recycled materials and so on, to control the cleanliness of the material. You see here different curves which we have measured at different filter sizes and different qualities. Here's another application which was used to see how good the screw geometry is designed to get a good dispersion of material. We have a compounder here with polymer and pigments filled in, and we have two filter test units which are mounted at different positions in a bypass to the compounder. We cannot run this test method like it is described in the standard 23900, because we cannot purge with the basic test polymer. We can run only the test material in the compounder, and so we have to evaluate also in this case the gradient of the filter pressure curve, and the difference between the gradient on these two positions give us a value how good the screw dispersed the pigments. Here in this example, we have measured the filter pressure values at 3 different processing points. Here we have run the system with 300 RPMs and at a throughput of 5 kilograms per hour. Here the second was at 600 RPMs with 10 kilograms per hour, and then 900 RPMs at 15 kilograms per hour. This means the loading was in all these 3 cases the same. And we can see that we have here the improvement of the material from the first test position to the second one. And we see that we have here the best filter pressure value at these parameters. And in this case, the shear rate was too high, and we damaged more the material than we could disperse it. So in this case, the processing parameters were not good for this application. Now we go to the film inspection. With the film inspection, we have a look on the film sample, scanning the sample with a camera. In the most cases, CCD or CMOS, CMOS line scan camera is used with different numbers of pixels, depending on the resolution and film width which we have to detect. Typical normally used pixel size are 4096. Also possible are area scan cameras which have, for example, a resolution of 256 up to 2048 pixels. As a light source, more the LED light source are used instead of the halogen light, which use also fiber optics. Special software evaluates the scan results and can classify the defects typically up to 10 different size classes and 10 defect types. In this example, we can use up to 14 defect features which we get from the system to use it for the classification different defect types. So we can separate or test gel particles, contaminations, and pigment agglomerates. We use, in the most cases, a resolution of 10 microns, and the resolution should be normally 3 times better than the smallest defect size which you want to detect. Here are some different configuration of the illumination techniques which can be used. Here we have the undirected transmitted light. The bright field method, where the camera is looking between two light sources in a black background, and the scattered light of the defect is detected by the camera. Here we have the configuration with directional transmitted light, which is parallel and passing the film and is detected by the camera. Or in the case that we have a very opaque material or colored material, we can use also the reflection method. But in this case, we can only detect defects which are on the surface. Here are some examples of the software. We see here the single detected defects, pictures of it, parameters which are evaluated. And here is a kind of map. This is the film, the running direction, and here is the film width. And here you can see the different positions of the defect which were detected, and the colors show you the type of defect which is classified in this case. The most important information in this case is the classification in size classes, and here's an example where we where we have here 10 size classes, and you see the distribution. A lot of small defects and only a less number of the bigger one. This is an example of a tabletop unit, very small equipment, where we have a chill roll here and the light source and the camera in this box. And here the film, which was tested, is winded up on a roll. This is a little bit larger equipment where the test area is protected by this chamber, and filtered air is blown into this chamber to protect this area against dust contaminations. But this unit can also be used on a normal blown film lines like here, or cast film lines which are open. But in this case, the resolution should be not so fine to avoid wrong results by dust particles. The next steps are the rheological measuring methods. The typical method is first to use a system where we run the melt flow through a melt pump to have a defined throughput, and then run a melt through a capillary, a round capillary, where we measure the pressure drop. And this system has, I will say, a limited range concerning the shear rate which we can use in this case. And so we designed also the wide range online rheometer, where we have a triple melt pump which divided the melt flow in 3 channels, where we can use simultaneously 3 different capillaries of different diameters, and so we can generate different shear rates simultaneously. And in this case, we can measure the viscosity curve over a wider range of shear rate. This is our newer product now, is also a mono online viscosimeter with 1 capillary, but in this case it can be mounted to a production extruder, especially for the recycling systems, where we have here the adapter which is mounted to the extruder, and we get here the melt flow from the extruder, and a melt pump this material through the capillary, and a second melt pump this material back into the extruder, so we don't lose material in this case. We monitoring, in this case, the pressure difference over the capillary, the melt temperature, and can calculate the melt viscosity. If we have measured also a calibration curve, we can calculate also the IV values, for the example for polyester materials, or the MFR values for other materials. We tried to integrate all this method together in a so-called multi-inspection system, which can be mounted to a big production line, especially recycling area or compounders. And in the bypass, we get melt flow, which we run through a melt pump in an online rheometer over a chill roll to a colorimetry system, then an optical inspection system, and behind the optical inspection system we have a near-infrared system which we use, and at last we have a model where we measure mechanical properties. This is here the multi-inspection system mounted in a bypass to our recycling line. The typical mass flow of this system is 2.5 kilograms per hour, and we run the material through a flat film die, which has a cross-section of 0.5 millimeter by 100 millimeter. The typical line speed is up to 5 meters per minute. This is the maximum, but the best performance which we get is with a film thickness of approximately 50 microns and the line speed of 2 to 3 meters per minute. We calculate the apparent viscosity because we have a rheological slot die integrated in the flat film die. And on the film we can also make the optical inspection with a resolution of 30 microns. And the calorimetry system, which I mentioned, gives us information about the LAB values. The NearInfrared system is a multispectral sensor, which has only a sensitivity of 5 to 10%. That's not so good for additives, but for the recycling area, is it enough to check whether the content of the material has changed. And then, as I mentioned, we have the measuring of the mechanical loads at the end of the line. And the dimension of the whole system is around 1.2 meters by 580 millimeters and 1.69 meters. The data can send to the production line via Profinet protocols, so that the production line can use this information quite quickly to optimize the process. This is a rheometer die where we have integrated here the slot die, and there is the slot for the production of the film. And here is the melt pump, which gives us the possibility to have a constant throughput, which is very important for our measuring. The calculation is very simple. We have the volume flow rate by the melt pump. Then we can calculate the apparent shear rate by the volume rate and the dimension of the dies. And then we can calculate the wall shear stress by the die geometry and the pressure drop, which we measure. And at the end, from these two values, we can calculate the apparent viscosity. As mentioned before, the multi-inspection system has also the calorimetry system, where we have a commercial color sensor integrated with has the possibility to use a standard white background for the calibration of the system, and which calculates then the delta L, delta A, delta B, and delta E values compared, for example, with your reference which you have set in the system. This is an example of the camera system with the 5 million pixel area camera. We have, in this case, the possibility to use different light methods, transmission, reflection, or both simultaneously, because we use 3 different LED light sources there. As mentioned before, we have a 30 micrometers pixel resolution, and the area which we investigate with one picture is around 50 by 40 millimeters. We can classify up to 5 different failure classes and in up to 10 size classes. And you can set the sensitivity of the system by setting thresholds and failure size. Here we see the camera, a small camera, and the covering over the light sensors. This is the near-infrared measuring system here, and there is the calorimetry system on this side. With the near-infrared system, we can detect different plastic types like polyamide and PE. It's very important to detect these different components in the recycling area to see how clean is my mixture which I recycle at the moment. As mentioned, the sensitivity of this system is not so high. The main reason is that we use a multispectral sensor but with 3 different diodes in specific wavelengths. So we have not the whole spectrum which we can use in this case. And this is at the moment a disadvantage. The sensor has to be calibrated by a special material mixture where you calibrate the system by your special mixture to see how are the contents of the different types of polymers. We think that we can, in the next year, start with a new system where we use an infrared near spectrometer, which has a full resolution in the area between 1,600 nanometers up to 2,500 nanometers, with a resolution down to 8 nanometers. So we have a much better possibility to measure more exactly data in this case. So the last point is the mechanical inspection of the system. In this case, we need a defined sample size. This means we have to cut the edges to get only the middle area of the film where we have a defined constant film thickness. And we measure this film thickness by a contact thickness gauge. And with these values, we measure also the mechanical load and can calculate the properties, the mechanical properties of the sample in this case. So that was the last point, and thank you very much for your attention. Is there some question or? No. Okay. Thank you very much.